Hello, welcome back to the Thermodynamics course. This is Lecture 2, and on the PowerPoint we'll look at the topics that we're going to go over today. And those two topics are, most of the time we're going to be looking at the equation of state, also known as the ideal gas law, and we'll also be taking a look at energy. We'll start with the variables in the equation of state. There are several different thermodynamic variables in this equation. It's a very important equation in thermodynamics. These variables can be rearranged, thus there are several different ways that the equation of state can be written. And the different variables in the equation of state, and we're going to go over each of these in detail, are the mass, m, the volume, v, the density, the mass divided by volume, or instead of writing it as density, it can be written as specific volume, which is volume divided by mass, the pressure, P, and the temperature, T, and there's also constants within the equation of state. On the overhead, we'll take a look at the equation of state and several different ways that this equation can be written. One of the more common ways is the first way here, where the pressure times the volume is equal to mass times the gas constant times temperature. When there's two terms next to each other there, it's understood that they're multiplied by each other. If there's a divide sign, then it means that there's division. In this case, it's all multiplication. We got two terms on one side of the equation, three terms on the other side of the equation. We can take the mass and divide both sides of the equation by the volume. When both sides of the equation are divided by the volume, the left side of the equation has just pressure, and on the right side of the equation, instead of mass that we had there, we have density, mass divided by volume. So we have pressure is density times the gas constant times the temperature. The specific volume is the inverse of density, or 1 over density. And when that is done, the specific volume symbol will go to the other side of the equation. So if we write it with specific volume instead of density, it becomes pressure times specific volume is equal to the gas constant times temperature. Now the pressure is the force divided by area. So we could also write this equation using what we have in number 2, except taking pressure and writing it as force divided by area is equal to density times the gas constant times temperature. And then number 5, another way that it can be written is that we can take the pressure times the volume is equal to force times the gas constant times T divided by gravity. We have an equation, force is equal to mass times gravity, where force was in a Newton, mass times acceleration. So also where there's force written in there, that can be replaced with an m times a g. Now this equation that we have here, number 5, is fairly similar to the equation that we have up here for number 1. PV is mRT. But you'll notice that there's a difference in that equation in that there's force and gravity written in there, where we can take this equation, F is equal to mg, and put mass on one side of the equation. So that's force divided by gravity is equal to mass. So that's how we change from this equation here to this equation by solving F is equal to mg for mass and plugging those terms in there. And there's several other ways this equation of state can be written. So you'll see several different types of equation, but it's all reverting back to the basic equation, which is PV is equal to mRT. On the PowerPoint, we'll look at the mass first and defining that and going over different characteristics. The mass is the amount of a substance. And the mass of any object is not dependent on gravity, although gravitational acceleration is going to have an influence on it. Mass and weight have separate definitions, where the weight is the mass times the gravity. The mass is expressed in the metric system in kilograms, and it can be written as mass is equal to force divided by acceleration. That's a rearrangement of force is equal to mass times acceleration. Another term is volume. Volume is a cubic measurement of a substance. Volume will commonly be expressed in meters cubed in the metric system. If it's a rectangular volume, it's length times width times height. If it was a perfect sphere, it would be 4/3 times pi, and there's a pi button on the scientific calculator. It'll be equal to 3.14 plus several other digits times the radius cubed. And there's additional methods of finding volume, such as if it's an irregular object, it can be displaced into water, and the amount of water that's displaced is equal to the amount of volume of that irregular object. Next, we'll look at density and specific volume. Density is mass divided by volume, whereas specific volume is volume divided by mass. Density and specific volume are inverses of each other. And how exactly is an inverse found? It's found by swapping the numerator and denominator, or by using the 1 over x function on the scientific calculator. When you take the density and multiply it by the specific volume, it's always going to come out equal to 1. And on the overhead camera, we'll take a look at how to find the inverse, and we'll look at that property of how it equals to 1 when they're multiplied. So suppose that we have the fraction 3/4. If we write the inverse of that, we exchange the numerator and denominator. So the 4 goes up to the top and the 3 goes to the bottom. So the inverse of 3/4 is 4/3. If it's written in the decimal point with a 0.75, this is the decimal form of this fraction, then we can find the inverse by taking 1 and dividing it by that decimal. So 1 divided by 0.75 is equal to 1.3 repeating. And the other property I mentioned is the density times the specific volume is always equal to 1. So if we have 3/4 and multiply by 4/3, we get 12 over 12, which simplifies to 1. If we take 0.75 times 1 over 0.75, then we end up with 0.75 over 0.75, which is also equal to 1. Or we can write 1 divided by 0.75 as 1.3 repeating times 0.75, and when that's multiplied out, that will also end up being equal to 1. Next, we're going to take a look at pressure. Pressure is the amount of force distributed over an area, and it's expressed in pascals in the metric system, which is newtons per meter squared. And the air pressure depends on the mass of the air above an area, and in this course we're going to assume that gravity is a constant of 9.8 meters per second squared. The next term is temperature. Temperature is the measure of energy that relates energy to the relative hotness or coldness of the object. It is a measure of molecular motion. So to determine the temperature, first a temperature scale needs to be developed. Once the scale is developed, that's where these terms hotness or coldness come into play. If it's a higher value on the temperature scale, then it's warming. If it's cooling on that temperature scale, then it's cold. Keep in mind that the words hotness and coldness are relative terms. The temperature can be expressed in kelvins or Celsius. When we're solving the thermodynamic equations, it's most common that you'll be using the Kelvin temperature scale since it's an absolute temperature scale. Absolute temperature scale means that 0 is the lowest temperature, so you can never have a negative Kelvin temperature, while on the other temperature scales it can have a negative value. That should say negative 273 Celsius is 0 degrees Kelvin. 0 degrees Kelvin is minus 273 Celsius. Next, we'll look at several constants that you will come across. Each individual gas has a unique gas constant, and R is the abbreviation for a gas constant. Now, there's different values of R that you'll run across depending on what type of gas that you're dealing with and different assumptions about that gas. The universal gas constant is R star, and that value is 8,314.3 joules per kilogram per Kelvin. And in this course, the two gas constants that you'll frequently come across, and we're going to go over how these are derived a little bit later, is the gas constant for dry air, RD. That's equal to 287 joules per kilogram per Kelvin. And there's the gas constant of water vapor, RV, which is 461 joules per kilogram per Kelvin. Avogadro's hypothesis. This hypothesis says that equal volumes of all gases measured at the same temperature and pressure contain the same number of molecules. So you take any gas and it has the same temperature and pressure, it's going to have the same number of molecules. It's not going to have the same molecular weight, but it's going to have the same number of molecules. Look more at that universal gas constant, R star. The universal gas constant, R star, is the same for any kilogram of a gas, assuming Avogadro's hypothesis is correct. R star relates other variables together in the equation of state. Average molecular weight is used to convert R star to R, and we'll go over how that's done. And again, R star is equal to 8,314.3 joules per kilogram per Kelvin. The gas constant for dry air, abbreviated RD, the apparent molecular weight of dry air is equal to 28.97 atomic units. And the air that's being looked at here is an average air sample in the troposphere, which is mainly nitrogen and oxygen and some argon. If you take the average molecular weight of that sample of air with that nitrogen, oxygen, and argon and other components in it, that average molecular weight comes out to 28.97 atomic units. So to convert R star to the gas constant for dry air, you take the R star and you divide by the molecular weight of dry air. And when that is done, we end with the value of 287 joules per kilogram per Kelvin. And on the overhead, we'll take a look at that division. We have our value of R star, and we divide that by the molecular weight of dry air, 28.97. And when we divide that out in the calculator, we end up with this value of 287 joules per kilogram per Kelvin. You'll run across this number several times this semester when solving equations, RD. And now you know where that number comes from. Next, we're going to look at the gas constant for water vapor, which is RV. RV is equal to R star divided by the molecular weight of water vapor. Now, we're assuming here that we have an air sample and it is completely water vapor. There's no other air within the water vapor. It's an air sample of 100% water vapor. The molecular weight of water is a little bit more than 18. Water is H2O, so it has 2 hydrogens, which is equal to 2 atomic units, and it has 1 unit of oxygen, which is equal to 16 units. So the 16 units of oxygen plus the 2 units of hydrogen gives us that molecular weight of water that's a little bit more than 18. We end up with a gas constant for water vapor, RV, is equal to 461 joules per kilogram per Kelvin. And on the overhead, we'll take a look at that division. We have our R star value divided by the molecular weight of water of 18. And when these are divided out, we end up with our 461 joules per kilogram per Kelvin. So if you run across this constant in an equation, you'll know now where this number comes from. Now we've covered a lot of information about the different variables in the equation of state, and now we'll go over how this equation was brought together. The equation of state is derived as a combination of Charles' law, Boyle's law, and Avogadro's hypothesis that we looked at. For Charles' law, there's the relationship between volume and temperature, and it's a direct relationship. And that relationship is volume is equal to a constant times the temperature. So if the temperature changes, the volume is going to change. Or if the volume changes, the temperature is going to change. For Boyle's law, the relationship is between pressure and volume. And in this equation for Boyle's law, the 2 terms are on one side of the equation. PV is equal to C. So in order for it to be a constant, to stay a constant, if pressure changes in one direction, volume has to change in the other direction because the value of C cannot change. It remains a constant. So C is that constant of proportion between the 2 thermodynamic variables. When we combine the Charles' law, Boyle's law, and Avogadro's hypothesis, we end up with our equation of state. Pressure times volume is equal to mass times the gas constant times the temperature. And as we've gone over, these terms can be arranged algebraically. Pressure can be expressed as force divided by area. And density or specific volume can be expressed by dividing volume and the mass terms. We're going to look at several of these relationships between the variables in the equation of state. If certain terms in the equation of state are held constant, then the relationship between certain other variables can be determined. And we're going to go over each one of those, starting with the volume-temperature relationship. Now, each one of these slides I'll keep up the ideal gas law, the equation of state, to reference that. The PV is equal to MRT. So if the mass and the pressure are constant, so in that equation at the top there, we're going to hold mass and pressure constant. When volume increases, then the temperature increases. since they're both increasing, or they could both decrease. If the volume decreased, then the temperature would also decrease. So there is a proportional relationship, which means a direct relationship. If one goes up, the other one goes up. If one goes down, the other one goes down. So there's a proportional relationship between the variables volume and temperature, and that is where we got Charles' law. The volume is equal to a proportional constant times the temperature. An example of this, I'm going to try for each one of these relationships to put an example up there so you can visualize in your mind the process that's going on here. Think of a hot air balloon where the air inside the balloon, the mass is fairly constant, and the pressure is fairly constant since that air can escape. The pressure will change somewhat, but let's assume that they stay constant. If they're both constant, if the temperature is increasing inside the balloon, you turn on the hot air and warm that air up, that air is going to expand since that air has more energetic motion. Warming air expands and becomes less dense. Since it's less dense, it's going to take up a larger volume. In the opposite situation, if the temperature decreased, then the molecules are going to slow down and get closer together, and the volume will also decrease. The next relationship that we're going to look at is between the pressure and the temperature. This time, we're going to hold the mass and the volume constant. When that's done, when the pressure increases, then the temperature increases. So there is a proportional relationship between the variables pressure and temperature. When one goes up, the other one goes up. If one goes down, the other one goes down. So the proportional relationship is pressure is equal to the constant times the temperature. And in a real-world example that you can visualize in your mind for this process here is to think of a steamer or a pressure cooker, where the volume of that pressure cooker is a constant, and the mass, the air, and whatever you're cooking in the pressure cooker is constant. So you've got a constant mass, constant volume. And then you turn up the heat in that pressure cooker. When the temperature increases, then the pressure is going to increase in there also. When the temperature increases, the molecules are going to be moving around more rapidly, and thus that is going to put more pressure inside of that cooker or steamer. The next relationship that we'll look at is the volume-pressure relationship. In this relationship, it's not proportional. It's actually going to be inversely proportional. We're going to hold the mass and the temperature constant this time. When the volume increases, then the pressure decreases. And if the volume decreased, then the pressure would increase. So there's an inverse proportional relationship between V and P, and that's where we got Boyle's law, where pressure times volume is equal to a constant. So if one goes up, the other one has to go down. An example of this is squeezing a balloon. And we'll go to the overhead, and I'll demonstrate this process. I have a balloon here. It has a constant temperature and a constant mass inside this balloon. And what I'm going to try to do is I'm going to try to change the volume of the balloon. I'm going to try to make the volume decrease. So I can try to make the volume decrease by pressing on the balloon. So I press my hands into the balloon, and notice what happens when I press my hands into the balloon. There's more pressure on my hands. The tighter that I try to squeeze it, the more that balloon pushes back on my fingers. So as I try to decrease that volume, the pressure is increasing. And when I let go of the balloon and let the volume increase, then the pressure decreases also. Next, we'll look at the density-pressure relationship. We can write the equation of state now. We took the volume and mass terms and combined them to produce a density. So we have pressure is equal to density times the gas constant times the temperature now. If the temperature is constant, when the density increases, then the pressure is going to increase. So there is a proportional relationship between the variables of density and pressure. If density goes up, pressure goes up. If the pressure goes down, then the density is going to go down. An example of this is pumping air into a car tire. So we're going to pump the air into the car tire slowly to keep the temperature constant. So you have a tire, it has a constant temperature air in there, but we're going to be pumping more air into the tire. As we pump more air into the tire, the density of that air in the tire is going to increase. We're adding more mass. The volume of the tire will change somewhat, but assume that the volume of the tire remains pretty much the same. As you're adding more mass into that tire, you're going to increase the air density. And since the air density is increasing, the tire pressure is also going to increase. Next, we'll look at the density-temperature relationship. If P is a constant, when density increases, then the temperature decreases. And this happens, keep in mind, because the pressure is staying constant. If the density increases at a constant pressure, then the temperature decreases. So there's an inversely proportional relationship between density and the temperature. So if the temperature increased, then the density would decrease. An example of this is cooling of air in a hot air balloon. So we have a hot air balloon, we've warmed up that air significantly, but then we stop heating the air. So over time, the temperature of that air in the balloon is going to cool down. As the air cools down, then the density is going to increase because the molecules are not going to have as much molecular energy. They're going to get closer together, and thus the density will increase. You could have the opposite relationship also. If you increased the temperature, then the density would decrease. Next, we'll look at the equation of state in everyday life, give you some more real-life examples of the equation of state in action. And 4 different examples that I'm going to show here and discuss. I'm going to discuss are the spraying of an aerosol can, and then talk about the basic mechanics of a refrigeration process. And then we'll look at a tire pressure example, and then finally a vacuum sealer. We'll go to the overhead camera and start with an aerosol can. Inside the aerosol can, the contents are under high pressure. The contents are compressed inside of the can, and the can will come into thermal equilibrium with the surrounding environment. So if the temperature in the room is 70 degrees Fahrenheit, and over time the temperature in the can is going to be the same also, 70 degrees Fahrenheit. So you have a high density, high pressure inside the can. And next, you spray the can. This can be a can of deodorant or Lysol, something like that. So you press it, and there's a violent expansion of some of the contents. Since it's in high pressure, as soon as you press this lever, this high pressure is exposed to much lower pressure air around it. And the movement is always going to be from high pressure toward low pressure. So while you activate this can temporarily, the contents are going to move from high pressure to the low pressure. And you're going to notice a volume expansion. So you have a small volume here inside the can. Once this contents comes out, then it expands rapidly and covers a large area compared to the size of the can. There also will be temporarily a rapid cooling, and you can feel this effect especially close to the can right as the substance is coming out. So if you put on, for example, spray-on deodorant, you'll notice that it feels really, really cold right when you're first spraying it. And that's because of this volume expansion, and when air expands rapidly, it's going to cool. Next, we'll look at basic refrigeration process. So for the refrigerator, we have a compressor, and what that means is it's taking air or a certain substance. It's taking a substance that has a smaller density and compressing it into a much higher density. When the substance is compressed, two things are going to happen. One, the temperature is going to increase. Rapid compression is going to increase the temperature. And also it's going to go from a gas to a liquid. They want to pick a certain substance that when compressed will turn from a gas to a liquid. And when a gas is converted to a liquid, this is a condensation process, you're going to have latent heat release. So not only are you going to have compression and warming, you have latent heat release. So you may notice in a refrigeration system that the back of the refrigeration system is somewhat hot. You may have hot coils back there. So this air is compressed, it's hot, but then over time it comes into thermal equilibrium with the surrounding environment. It gives off the heat to the surrounding air and eventually cools. And then over time you're just left with a highly compressed, cooler liquid. And then the next process is to take that compressed liquid and then cause a volume expansion, a rapid expansion of that liquid. When a volume expansion occurs, just like in the aerosol can example, there's going to be a rapid cooling. Also, you have a latent heat transformation. You're going from a liquid to a gas. So this is like an evaporation process, evaporational cooling. So you have latent heat absorption. So this process in here is what cools the air down inside the refrigerator, the substance undergoing that volume expansion and latent heat absorption. And then the cycle repeats itself over and over again, where the excess heat is given off to the air outside the refrigerator so that it can cool off the air that's inside. Next, we'll look at tire pressure. Suppose we have a tire here, and we have a high pressure air, and it has a high density. And now we're going to let the air out of the tire. If you let the air out very quickly, then you're going to have a rapid expansion and you'll have cooling of that air. It's like the aerosol can, where you had the high pressure, high density air, and when the air is allowed to come out, you have you have lower pressure air surrounding it. The movement is from high pressure to low pressure, and then you get expansion and cooling. And another example is that of a vacuum sealer. Suppose that we have a confined space here, and we take a pump out here that's going to remove the air from inside this confined space. When that is done, the pressure is going to go down, and since mass is being removed, the density is also going to go down. If the walls can contract, then the volume is also going to go down. If you removed all the air, then all these terms would go down to zero, where there'd be zero volume, zero density, zero pressure. But if these walls here cannot contract, then the V will remain constant, and if you removed all the air out, then you'd be left with a vacuum inside with no air pressure inside the space. Next, we're going to apply the equation of state to the atmosphere. Looking at an air parcel in the atmosphere. An air parcel, it is a volume of air in the atmosphere with similar temperature and moisture characteristics throughout. The air parcel will follow thermodynamic principles as it rises or sinks. In an adiabatic process, you'll come across that term several times in this class. In an adiabatic process, the parcel is assumed to not mix with the surrounding environmental air. The pressure, the volume, and the temperature are all going to change as the parcel rises or sinks adiabatically in the atmosphere. And the term M will remain constant since we're assuming adiabatic conditions where there's no heat, mass, or momentum flowing into the parcel or out of the parcel. If the parcel is rising, then the pressure will decrease, the volume will increase, and the temperature will decrease. And if the parcel sinks, you'll have a vice versa of that process. And on the overhead, we'll take a look in a little more detail this process. Often a parcel of air will be drawn as a bubble. So we have a bubble of air which has different thermodynamic characteristics from the surrounding air. It may have a different temperature, may have different moisture characteristics, or both, as compared to the surrounding environmental air. So the air inside of this bubble here we refer to parcel air. The air outside of it is referred to as environmental air, or the surrounding environment. So we have a parcel of air that initially has a volume, a pressure, and a temperature, and we're going to lift this parcel of air up higher into the atmosphere. When this parcel is lifted up, the volume is going to expand. And the reason why the volume expands is the air surrounding the parcel here has less pressure than it does down here. When you're near the surface, the air pressure is higher surrounding the parcel. But as the parcel rises upwards, it's surrounded by lower pressure, so the parcel is going to expand into that lower pressure, just like spraying the aerosol can produce an expansion of the air because there's less pressure surrounding that mass. So since the volume increases and the molecules spread out more, then that causes the pressure inside the parcel of air to decrease. And the temperature is also going to increase. If this is a dry parcel, it's going to decrease in temperature at the dry adiabatic lapse rate. If it's a saturated parcel, it will decrease at the moist adiabatic lapse rate. Next, we're going to look at what is energy. Energy is force that produces motion. Energy is described as the capacity to do work. The basic equation for energy is work is equal to force times distance. There's several terms you'll run across: energy, work, and heat. These are all describing a similar process. They're describing the movement or potential movement being applied by a force. And they all have the same units. Energy, work, heat all have the same units of joules. Energy conservation. The total energy within a system is going to be conserved. The energy can transform to another type of energy, but energy cannot be created and it cannot be destroyed. There are several different types of energy that I'm going to go over with next. Those are potential energy, which is stored energy; kinetic, which is the energy of motion; gravitational, which is energy by position within a gravitational field; and molecular activity, which is going to influence what the temperature is of a substance. Energy within the fluids. If it's a gas, as energy increases, the molecular motion increases. The molecules are moving faster and colliding into each other more as the energy increases. Liquids, the same as the gases, but there's a tighter spacing of the molecules. Molecular collisions are more of a vibration in liquids, since molecules are linked to each other much more closely than they are with a gas. Results of increased heat. So if you're adding more energy to a substance, this is the result that can occur. You could have a temperature increase if it's a sensible heat process. Sensible means that you can measure it with a thermometer. If you can measure the temperature going up. You could have expansion if there's an increase of heat. And expansion will occur if the volume can change. In some situations, the volume may not be able to change, but the volume can change. Then if you add heat, that's going to cause an expansion, such as you take a parcel of air, you add a heat to it, it's going to expand and become less dense. Or a phase change can result in an increased heat if it's a latent heat process, such as condensation releases latent heat to the surrounding environment. Here's the energy transfer equation. That is, heat is equal to C, a specific heat constant, times the mass, times the T1 minus T2, where T1 is the initial temperature and T2 is the temperature after the addition of heat. This heat transfer equation is used in the equations that you'll run across in this class for thermal equilibrium, when figuring out when two substances come in contact with each other, what temperature they'll have at thermal equilibrium. Transmission of heat. Heat can move by conduction, which is a flow of heat which are in direct contact with each other, such as think of a stove. You put the pan on top of the stove warms up, the pan warms up because it's in direct contact with the heat of the stove. You can have convection, which is a very important process in the atmosphere. It's one of the primary ways that heat is transmitted in the atmosphere is by convection. That's the mixing of substances with different amounts of heat. So if substances have different densities, and they'll often try to mix together. Think of like a convective type motion where the hot air at the surface warms up and it wants to rise up with air aloft. So you get a mixing of the air. And then another process is radiation. This is the movement of heat by the use of electromagnetic waves. So this is how the sun warms up the earth, by transmitting the radiation and by the earth absorbing that radiation. And in the atmosphere, the Earth's surface absorbs a lot of that radiation, so that's why temperatures near the surface of the atmosphere tend to be the warmest, and as you go up in the atmosphere, it tends to get cooler and cooler because you're getting away from that heat source, the warming of the Earth's surface. Next, we'll look at specific heat. Specific heat can be defined as the amount of energy needed to raise 1 kilogram mass by 1 Kelvin. Water has a relatively high specific heat, since it takes a relatively high amount of energy to raise 1 kilogram of water by 1 Kelvin. Heat and gases. When heat is added to a gas, it will usually expand and increase in temperature. Gases readily expand or contract when heat is added or subtracted, since gas molecules are in free motion. For a given gas, an increase of heat into the gas will generally cause it to decrease in density. The last thing that we'll do is we'll look at the equation of state and different weather processes. For each of the processes below, we're going to explain how the variables in the equation of state could change. There's 4 different scenarios that we're going to look at: rain falling into dry air and evaporating, 2, solar radiation warming the boundary layer, 3, a downsloping wind, and 4, rising air within the entire troposphere. We'll start on the overhead camera with rain falling into dry air. So we have an air parcel here, which is going to be a box this time. So this is our air, our dry air, and we have rain falling through that dry air. So within this box, you're going to have evaporation taking place. Evaporation is a cooling process, so the temperature would be expected to fall, a decrease in temperature. The density would be expected to increase. Since you're decreasing the temperature, then the molecules are going to get closer together. So that is going to increase the density. If the density increases, the volume is going to decrease somewhat. The mass and pressure are not going to change very significantly. The mass may change somewhat because the evaporation of water is adding more air molecules, but then that'll produce some expansion of that too. But the far more important process is the temperature decrease. The temperature decrease is a more significant process than the increase of mass due to adding the water vapor molecules that are evaporating. Solar radiation warming the boundary layer is next. So we have our surface. This is our air near the surface, and here's the sun warming up this layer of air here. We would expect the temperature to go up. Temperature increase, adding that solar radiation. Since the temperature is going up, then that air is going to expand. When the air expands, then the volume is going to go up, and the density is going to go down. The air is going to become less dense. So those are the significant processes occurring here. So this air will become less dense. If it warms up enough, then it'll start rising upwards, and then you'll also get convective processes too. And if the atmosphere is unstable, then that can lead to clouds and thunderstorms. If it's stable here aloft, then the air will just mix here down close to the surface. Next, a downsloping wind. We take a parcel of air, our box here at a higher elevation, and we move it down to a lower elevation. So the box is surrounded by lower pressure than it is down here. When it moves to closer to sea level, to a lower altitude, it's going to be surrounded by higher pressure. So the pressure within this box, the pressure is going to go up, an increase in pressure, since the surrounding air has higher pressure, and it's going to force a compression of that box. So the volume is going to go down. The temperature is going to go up. You have an adiabatic compression process occurring. The pressure is increasing, causing the box to be squished closer together. So the molecules are getting closer together, So that increases the temperature. And since the box becomes smaller, then the density is going to increase. Last, we look at rising air within the entire troposphere. So we're at the surface here, and we have, initially, we have air that's not rising. And then we set it into motion. As this air rises near the surface, air will come in to replace it, and the aloft air will diverge out to leave. The important process here is that when the air is rising upwards, that the temperature is going to go down. You're going to have a cooling that takes place. Since this air cools, then the density is going to go up, and the volume is going to go down. So think of this as like a low pressure region or low heights aloft. When you have rising air, it's going to cool this column of air, so this column of air is going to shrink down because it's cooling. So you're going to have lower heights, lower pressure, where you have an area of low pressure or very cold air. If you have very cold air here aloft, you'll notice lower heights. That is going to conclude this lecture for today. Study all your materials, and I will see you back here next day.